In this lecture, we are going to discuss rotations in quantum mechanics. This is deeply connected to a somewhat more familiar theory, the theory of angular momentum in quantum mechanics, and we are of course going to touch on that as well. But first, let us point out that the theory of rotations in quantum mechanics is a special but very important subcase of a more general theory, the theory of coordinate transformations in physics. Now, this particular subclass, the theory of rotations, acquires special importance because it is firstly connected deeply to the theory of angular momentum, and angular momentum is an important physical quantity, and secondly, rotation is an important symmetry transformation in physics. In fact, these 2 points are actually linked, because the reason why angular momentum is really so important is because rotational symmetry is an important symmetry transformation in physics. But before we get into the theory of rotations, first let us look at a bit of a general theory, the theory of how fields, in particular a scalar field, transforms when we transform coordinates. So the question that we have here is, suppose I have a scalar function u, which is a function of x, y, z. Of course, this describes a scalar field, a scalar quantity defined at all points in a region at least. Now the question is, how does the scalar function, which describes perhaps some physical quantity, change under a coordinate transformation? The transformation I am denoting by r, which here we say denote this way: x, y, z, the coordinates under r goes to a new set of coordinates x prime, y prime and z prime. Notice that what we are saying is here is what changes are the coordinate labels for a point, not the point itself, and certainly not the physical quantity which is associated with a particular point. Now this, in a perhaps an indirect way, means that the function which describes the physical quantity must change when we are changing the coordinate labels. So u of x, y, z must change to a new function u tilde of x, y, z, and u tilde is something which we get when we apply the transformation t on the function u. So what we are saying here is corresponding to a coordinate transformation r, which acts on coordinate space. There is a transformation in function space which acts on functions to give you a new function. So u tilde of x, y, z is of course the same as the function tu at the point x, y, z. Now this change has to happen, but it has to happen in a very, very specific way. Remember, the point stays the same despite the fact that x prime, y prime, z prime become the new labels. So value of u tilde, so the function u must change into a new function u tilde, but this change has to happen in a very specific way. After all, remember that the point has not really changed. The same point which used to have labels x, y, z before now have labels x prime, y prime, z prime. Neither has the physical quantity changed. So u tilde evaluated at x prime, y prime, z prime is the value of the physical quantity at the same point that was being referred to as x, y, z before. So it has to be u of x, y, z. This means that u tilde at the new coordinates r acting on x, y, z must be u of x, y, z. So what does this tell us about the function u tilde? The function u tilde evaluated at x, y, z must be the same as the function u, but evaluated at the point which became x, y, z after the transformation, that is the point r inverse x, y, z. You should notice that this statement here and this one here are effectively the same statement. U tilde at r x y z is u at x y z, and hence u tilde at xyz has to be u at R inverse xyz. So this is the rule that we have come up with for transforming a scalar quantity or a scalar field. U tilde, the new function describing the scalar field, which is the same as tu, the transformation t acting on u in function space. This new function tu at xyz has to be the old function u at the point R inverse of xyz. Now if you think about this a bit, I'm pretty sure you will be able to convince yourself of the reason for this. Still, there may be a nagging doubt as to why do you need the R inverse, why not R? So let us try to see this from a different point of view. Let us consider now, instead of one transformation, two successive coordinate transformations. So xyz gets acted upon by the transformation R1 to produce x prime, y prime, z prime, and that in turn gets acted upon by R2 to produce x double prime, y double prime, z double prime. Now of course I can think of these two successive transformations as a single transformation, one which takes you directly from xyz to x double prime, y double prime, z double prime, and that single transformation is what we call R2 R1. Note, in our notation R2 R1 means R1 gets to act first, then R2 gets to act. Now the question is, how does the scalar function u of xyz transform under this set of successive transformations? Well, when you applied R1 on xyz, u xyz transformed with the corresponding transformation, let's call that T1, to a new function u tilde of xyz. Then we applied R2 on the coordinates. U tilde xyz got acted upon by T2, the transformation corresponding to R2, and this leads to the new function u double tilde xyz. So that's the next scenario. Xyz is going to x prime, y prime, z prime under R1, and x double prime, this is in turn going to x double prime, y double prime, z double prime under R2. On the other hand, in function space, at the very same time, what happens is u xyz goes to T1 u, which we call u tilde of xyz, and that in turn goes to T2 of u tilde, that is u double tilde xyz. So u double tilde xyz is T2 of u tilde xyz. Remember, u tilde itself was u1, T1 acting on u, so this is really T2 acting on T1 u of xyz, and the way we define composition of transformations, or what we usually call product of transformations, is simply one transformation gets to act after the other. So this thing T2 acting on T1u is denoted simply by T2 T1, the so-called quote-unquote product transformation acting on u. So u double tilde at xyz is nothing but T2 T1 u acting on xyz. On the other hand, we already know what the transformation is like in terms of the coordinates. So u double tilde xyz, which we got, remember, when the coordinate transformation was R2, has to be the same as the previous function u tilde, but acting upon R2 inverse xyz. But then what is u tilde? U tilde is what you get when you apply the coordinate transformation R1. So it's u at R1 inverse acting on the coordinates. So u at R1 inverse, R2 inverse of xyz. However, we know one thing from elementary algebra. If you want to invert a succession of transformations, you have to apply a succession of inverse transformations in opposite order. This is easy to understand from everyday life. Remember, if you want to wear your shoes and socks, you wear the socks first, then you wear shoes, but when you open them out, you have to open out the shoes first, then you have to open up the socks. So in order to undo the effect of R2, R1, you actually have to apply R2 inverse first, then apply R1 inverse. So R1 inverse, R2 inverse is actually the inverse of R2, R1. And this means that U double tilde T2, T1 U acting on XYZ is U at R2, R1 inverse XYZ, which is exactly the transformation you would have got corresponding to R2, R1. So the upshot of all this is, if R1 corresponds, R1, a transformation in the coordinate space, corresponds to T1, a transformation in the function space, and R2 corresponds to T2, then the successive transformation or composition transformation R2, R1 in coordinate space has to correspond to the corresponding quote unquote product T2, T1 on function space. If I am allowed to use technical language, this really says that the transformations in function space furnish a representation of the group of transformations in direct space, in coordinate space. If you don't understand this particular statement, don't worry. We will not be using this group theoretical language for the rest of the lecture. However, if you know any group theory, you would realize that this is exactly where group representations arise from in physics. And this is why group representations are so important when we talk about the application of group theory to physics.